All right, welcome back. So we're going to start taking a look at our different data storage components, whether it's hard drives that are internal or external. We're going to take a look at RAM as well, because that's some type of storage. It's just volatile, so it's not always there. We're going to look at troubleshooting those components, different types of RAM, and then we're also going to talk about this thing called RAID. And we are not talking about the bug spray, but the redundant array of independent disks, which is something you will come across once you get a job in an enterprise environment or a big server farm. So let me go ahead and share my screen and we can get started. All right, so the first thing we're going to work on is identifying different kinds of RAM and the features of them, the different kinds per se. And then we're going to look at how to troubleshoot it if we come across any issues. We need to make sure we can install and configure and manage any of our storage devices, whether they are long-term or short-term storage. And of course, that comes with firmware because it's something that we're plugging in. And the last part that we'll talk about in this section is RAID. So I want you to be comfortable with what is RAM. Well, RAM is memory. It's literally just a printed circuit board that holds different chips, and it all acts as a single unit. So there are slots on your motherboard that we took a look at. They are removable as far as your RAM, removable from those slots, and replaceable, which means you can upgrade. So different types of RAM is something that you should be aware of, and you'll see on screen DDR, DDR2 and 3. DDR4 and 5 are real things, and they are they're here. They're on our computers. They're in our computers. They're usually actually in our graphics cards, is where you see the DDR5 is being implemented a lot now. But DDR literally stands for double data rate, and so it's able to double the amount of data that is processed per clock cycle. And all that means is every time the system makes a decision or a process, this can actually do twice the work. So there are a certain amount of pins that you may have a question about in your practice tests. And you want to know that DDR2 and 3 have 240 pins. And that just is something that you want to be aware of in regards to, is it compatible with the slot that you actually connected in or connected to? So on the motherboard, you need to make sure that it's compatible. That's the whole point of all of this good stuff. So we do have single and double-sided memory. And literally, this is not necessarily that single-sided memory only has one side of it. So don't take it that literally. But it is an expansion of the ability of the RAM for how much it can hold, how much information, how much data is accessible to the computer at any given time. Double-sided RAM literally just has 2 memory banks, and only one side at a time can be accessed by a computer, so it doesn't increase the speed or the rate, but can be held. ECC is error correcting code. So some RAM, expensive RAM, RAM that we put in servers, has ECC on it or enabled, meaning that it can actually check the bits, the ones and zeros that are on that thing, and make sure that it's not corrupted, that our data is accurate, it hasn't been modified, or it hasn't been broken in any way. And it does that using a parity bit, which is the 9th bit in our byte. So a byte is made up of 8 ones or zeros. And when we use this thing called parity, which we will definitely talk about more later in class, it has a 9th bit, and that's our error correction or error detection bit that we kind of just have tagging along at the very end of our 8 bits. So different types of RAM. DDR is one of the most common things or verbiage that you'll see when it comes to RAM, and that's just double the data rate. But ECC is not something you'll come across as often, but definitely valuable in an enterprise or business world, because error checking is one of the greatest things we can do to ensure our data is not corrupted as it's transferring out and along. Different types of configurations. Different chipset configurations within RAM will literally determine how fast data can be transferred between any of the chips on the board. So the slowest one is single channel, the fastest is quad channel. But in their single channel, it's limited to only one data channel for communication, meaning it can do one thing at a time. If you have a double channel, it can transfer twice as fast because it has two different data channels, which means you can send and receive data simultaneously. Triple channel is faster, uses 3 channels, it's 3 times as fast, and quad channel is faster than that, and it's 4 times the rate of a single channel RAM configuration. So nothing super complex here, just understanding that you do have options to increase the performance of your RAM. Now, parity is something we talked about. Sorry about that, I flipped over too many slides. Parity versus non-parity. Now again, that's that one extra bit. Whenever parity is used, the data transmission has 8 bits of data, and then there's a 9th bit that's being added, and that 9th bit is the parity bit. And all we use it for is to determine if a piece of data is equal to another piece of data. So how this works in summary is that the bit value can either be true or false. 1 is true and 0 is false. And if an error is detected and the 2 strings of data don't match, that means that it's going to throw it out and identify that a piece of data has been corrupted of some kind. That byte, those 8 bits, have not passed their check. So it's pretty rarely used, but again, in ECC, that's how we make all of this good stuff come together. So buffered and non-buffered RAM is pretty simple. So buffered RAM contains an actual control chip, and that helps the memory controller when there's a lot of memory installed in a system. So at your computers at home, you have 2 sticks or 4 sticks of RAM. This is not where that's happening. Again, this is in an enterprise, big business, server farm type environment. So it's usually just used in servers to make sure that all of the data is handled correctly. It's kind of like having a piece of middle manager involved to make sure that everything is going smoothly. Coordinating, managing, looking at where there is an issue, and then making you aware of any problems that do come up. So buffered RAM usually contains an ECC or memory, meaning again it works with those higher end server environments that you're going to have that error correcting code. It helps find errors, it helps correct errors, and that is definitely more expensive than your non-buffered version of it. So non-buffered RAM is where you take out that middle manager and you're able to communicate directly from your memory to the chips on the board or the circuitry on the board itself. So less expensive, a little bit faster, but not as much management or oversight. We are going to talk about compatibility a lot. You'll hear me say it many, many times. I know you'll get sick of it, but it's such an important piece, not only for your test, but in real life as well. So I want to take a look here at 3 different things that are really specifications that you need to make sure are compatible when you're installing your RAM or choosing the RAM to install on your computer. CAS latency, CAS. It just stands for column address strobe. This is literally how the processing signals go from your memory circuit and are found, and how fast the information can be found. So how much lag time, or the opposite of that, is how fast is it? So how many clock cycles it takes to see the results is how much time it takes to grab the information. So when you see RAS or RAS below that, it's much like your column address strobe, but this is actually your row address strobe. So looking at data, just like an Excel sheet, you have columns and rows. Your data is housed in the same way in your RAM. So after you send your memory controller a specific address, how many rows it has to go through is your row address strobe, and then how much time it takes to get there is your column address strobe. Pretty easy stuff. Row pre-charge time is not something you need to know for your test. Your RP time that you see there, active time is the same thing. But if you're going to be a hardware specialist and you are building computers and building servers, This is going to mean a lot to you in real life. If not, this is information that is a little bit above and beyond what you need for your basic A+, but it's good stuff to know. So row pre-charge time, or RP time. If a row is already selected in our row address strobe or RAS, this is going to tell you how many cycles have to pass before you can actually go to the next row. Meaning once a piece of data is found and communicated, how much time do you need to wait until you can go to the next one? Row active time is literally the minimum number of clock cycles a row needs to be active to make sure there's enough time to access the information. So if I'm going through a row at the grocery store, how long is it going to take me to get from the beginning of that row to the end of it and go to the next one? Even if the cereal you're looking for is on the top right, maybe 3 shelves in, if you're running down the row, you might miss it. So in all reality, we know that we have a certain pace that we can keep. This is the same thing with our RAM. How fast can we go down that row and still make sure that we're using our time efficiently? So straightforward stuff, probably new verbiage for you. I don't want you to stress out too much on these details, because I'll tell you that unless you are building computers or servers, this is not something that you're going to come across very often. And this level of detail or granularity will not be on your test. So we have our RAM installed. We made sure that it's compatible. Now we need to know what issues we might come across. So one of the first ones here is ESD. So that electrostatic discharge is what ESD stands for. And that's when you walk across the carpet and zap your brother or sister, or you rub a balloon on your head and your hair starts going crazy. If you zap a piece of RAM or pretty much any component, you're going to have an issue. You could actually cause damage to that component to the point where it doesn't work anymore. So that's a cause of an issue that is a cause that would lead to crashing or lockups and have your RAM completely fail. Another one that you're looking a little bit further down is your blank screen at boot up. This will be caused if you don't pass your post. Now, the normal response that you would get is actually a really loud beeping noise, and that's the one that you see right below that. Now, post errors most commonly are actually caused by RAM not being seated correctly, meaning not being clicked all the way into their slot properly. So that's one of those things that you want to look out for if you start hearing beeps when you boot up your computer, or for some reason everything just goes blank. The first thing you want to check on your motherboard is for your RAM to be where it's supposed to be, all the way clicked into place. So we have different storage devices, and we did a quick overview of these in our initial chapter, but let's talk about the considerations that we have to have here. So you have internal and external devices that we can store data on. We have CDs, we used to have floppy disks that we don't use too often anymore. Of course, we have USBs and flash cards, and all of those things are removable storage or external storage. Now, of course, we have our internal drives as well, and that's internal storage. So our disk drives, our solid state drives, and all the good things that are inside of our computer. What I want to talk about is what considerations we have to look at when we're choosing the best way to store our data. So when we're looking at internal, we want to make sure that it is compatible, you hear that come up again, compatible with the computer. Does the computer already have an internal storage device, or do we need to install one? If we're going to install one or replace the one that's already there, does it actually physically fit is a question that you should be looking at. What type of control or power or ports do you need? Meaning that if you have a SATA drive, do you have a SATA slot open on your motherboard to plug this thing into? Does it need its own power? Do you have a power slot on your drive to plug it into? Do you have enough power coming through your power supply unit to make sure that that internal drive can operate without any issues? So those are all the things that you want to look for inside internal storage. But we can also have external storage, and some of the questions are the same and some of them will be different. So when we're looking at external storage, again, do you have the ports? If you're going to get something that connects via USB, do you have an open USB port on your system to plug this thing into? What if your external storage device uses FireWire instead of USB? Do you have the capability of plugging it in anywhere? Do you need an adapter, or maybe you should be looking at a completely different drive? Power source. I think one of the funniest things, and something I come across pretty often, is that a company will upgrade and buy all this cool new stuff for their employees, and they don't realize that they have nowhere to actually plug it in the wall, meaning that all the power sources are already used, one for the system and one for the monitor. Maybe something else is plugged in there, but they might buy 500 of these cool units that they want to plug in at everyone's desk. And now they're having to buy between 200 and 500 surge protectors or multi-outlet connectors to make sure they actually even have a place to plug it in. So keep those things in mind. They're simple, but they can be very costly mistakes. So now that we're plugging all this stuff in, we want to make sure we actually manage it. And the utility in Windows is called Disk Management or Computer Management Screen. And you want to be able to go in there and see all the drives that you have installed, internal and external. And when we get into partitioning, this is where all of that magic is going to happen. So you'll see on screen is just a screenshot per se of our C drive. You see that there are different partitions. You can see the size of the drive. You can see the file system it's using, NTFS for all the ones on screen here. There are different file systems, and we'll talk about those. But you can see the drive letter of it. You can split partitions. You can add drives from this screen. You can add an array, and we will definitely talk about that as well during this chapter. So there's lots of things that you can do here, but it's 100% dedicated to managing the drives and disks and storage areas that you have on your computer. So I mentioned bug spray, and that is when we're going to talk about RAID. There are different types of RAID and different numbers that are going to be associated with it. So let's talk about what it is, and then we'll get into the details. RAID stands for Redundant Array of Independent Disks. So there are lots of different vendors and they have different specs for it, but the goal is to increase performance and or what we call fault tolerance, meaning we're going to increase redundancy. Now, listen to when I said and or. You could have RAID implemented to increase only performance. You could have RAID to increase only redundancy. However, you could implement a different type of RAID, which would increase both. And those are usually the ones that are seen as the best option, but it just depends on your system, your configuration, and your goals. So when we take a look at how we're going to implement this, there are two different ways. We have software RAID, which means you're going to operate this through your software, through your operating system. And we have hardware-based RAID. Now, where I'm going to focus, to be completely honest, is on the hardware-based RAID, because you'll have different physical drives and a controller that you will be really making all of this happen, configuring it and managing it and coordinating it through. So you need to make sure that you have a motherboard that is capable of this, compatible with this, and we can take a look at the different RAID levels and see how all this good stuff works. So RAID 0 is called striping. And I'll actually take you guys out of the PowerPoint when we get done and do a quick rundown of how this all works. I'll actually write it on screen for you. But RAID 0 implements what's called striping, and that means we're going to spread data across three or more disks. Nope, 2 or more for RAID 0. And what this does for us is nothing as far as increasing our redundancy, which means if one of my drives fails, all the data is gone from that drive. So even though I have 2 disks, I am not creating any redundancy with RAID 0. I'm striping the data to increase performance. That means my system can run faster and I can get data back faster when I request it from a storage place. Now, RAID 1 is going to do everything for me in regards to creating redundancy. Now, this also uses 2 disks, and what we're going to do here is mirroring, and that's actually what RAID 1 is called, is mirroring. So everything that I have on disk 1 will have a mirrored copy on disk 2. Therefore, if one of my disks fails, I can still have a complete copy of everything that's going on in real time on my second disk. This does not make my system any faster. It could actually make it a little bit slower, but it creates redundancy, and that is important. Now, RAID 5 uses 3 disks, 3 physical drives, and they can be the same capacity and same type of drive, and it's actually preferred if they are. Now, this is going to incorporate striping. However, we're also going to use parity, like we talked about, that 9th bit. A third of all of the information that you have is going to be saved on each drive. So the goal is to spread this out equally across them and make sure that we can have an increase in performance. But what does that do for us as far as redundancy? Well, that's where the parity is used. If one of the drives fails, the parity information for that drive is actually kept on a different drive, so we can use it to reconstruct any of the data that we lose. Now, again, that's kind of hard to understand just when I'm talking about it, so I'm actually going to draw it out for you at the end of the chapter so we can take a look at how this actually works. RAID 10 is the last one you see there, and that is actually RAID 1 plus 0 is how that's written in the most correct form. That means that we're taking striping and mirroring, the best of both worlds, and combining them together. Now, how many disks did we need for RAID 0? 2. And how many disks did we need for RAID 1? We needed 2 there as well. So we need a minimum here for RAID 1 plus 0, a minimum of 4 disks. 2 of them will be used for striping, meaning that it's going to increase our performance. The other 2 disks will be used for mirroring, meaning that it's going to provide complete redundancy. This is great because now we have the best of both worlds. And if you look at the screen, you'll see a minimum of 4 disks. You can definitely use more than 4 here, just depending on how much data you're trying to store. So now that we have all this cool stuff plugged in, we have redundancy in our data, we've increased how fast things work, well, we have to tell it all what it is, right? So we touched very briefly on what firmware is, and I want to go more in depth here. So what is firmware and how all this good stuff works? Well, firmware is not quite hardware, but it's definitely not software. It's specialized, and it's stored in a memory chip on your motherboard. And it's usually written from on a reprogrammable chip. So anytime you have an update, if an error is found or something is corrupted, the manufacturer can send out a firmware update. So firmware is that middle area that connects your hardware to your software. But it's not considered either one of those things exactly. It's the script that allows all of that good stuff to happen. So let's take a look at, in the BIOS and the UEFI, how this works and how this connects. So I'm going to give you a quick second here to remember what BIOS stands for. Let's see how you're doing with your vocabulary. All right, BIOS stands for Basic Input Output System, right? BIOS is very, very important. So if you take a look off the screen, of course, when I ask you this good stuff, and make flashcards if this is the first time you are seeing it or remembering those acronyms. These are great things to practice, and they will be on your test. So what does firmware do, or why does it matter how it relates to BIOS? So the BIOS memory actually stores information about the computer setup, and that means that the system firmware gets referred to every single time when a computer starts. It needs to know that the keyboard is still there, that the mouse is still there, all the peripherals that are plugged in are still there, all the system options are still the same, and that it has a healthy environment to operate in. So every time the computer starts up and accesses the BIOS, it's also accessing the firmware for everything that it's interacting with, all of their components. Now, in regards to The UEFI, again, that's just the upgraded version of the BIOS. So the same exact thing is going to happen here, and the same dependency is taking place, where anytime you boot up the computer and you get to the UEFI screen, if you choose to go in there, the same startup procedures are happening, and that means the firmware is being checked. And if any upgrade is needed, there's a process. Why would we ever need to do an upgrade to our firmware, and how can all this good stuff go wrong? So firmware is going to be upgraded anytime that new hardware is installed. You're going to need the firmware for it. But if there's an issue, whether it's just a quick fix or a corruption is found, most recently you'll see a lot of firmware upgrades to patch security issues. That means you're going to have a firmware upgrade. Any new features that are added, like plug and play or changes to be within compliance, those can come from firmware upgrades as well. But I want you to be careful in regards to downloading firmware from third-party sites. Anytime you have a piece of hardware or peripheral that you're plugging in, your drivers are definitely going to come from those third-party sites. Your firmware should come from the third-party site of the manufacturer, not just a random place where you find it. So be careful when you're Googling out there for just firmware updates. You may come across things that are corrupted, that include viruses, spyware sometimes. This has been a major issue in hardware over the last 2 to 3 years, especially with routers and switches. So what are the components that have firmware and what do they use it? So again, anytime you start up your computer, your firmware is activated, and every component needs to be accounted, present, and checked per se to make sure that it's accessible via the system, and this happens during the boot process. Anytime you want to make a change to a hardware component, you need to make sure you check the system firmware settings, and if any changes or upgrades are needed, you have to handle those accordingly. Firmware is every peripheral, but it's also the things that are directly connected to your motherboard, meaning your RAM, any of your drives, internal or external, your optical drives, reading CD, DVD, or Blu-ray, as well as your CPU chip itself. So what are the configuration options, and why do we care so much about this? Well, anytime you configure your firmware, you're making an alteration to it per se. And this is something that you are not going to do often, but it's something that every component and peripheral device depends on. This is the script or the code that contains its life instructions. When you wake up in the morning, you know that you're a human, not a dog or a cat or a tiger. And you know that your arms are where they're supposed to be, your legs are where they're supposed to be, and you can use your legs to walk and your hands to grab things. Imagine waking up not having any of that information every morning and having to rediscover. Kind of like 50 First Dates, but even more intense. That would not be fun. So that's what our firmware does for our computer. It tells it what everything is and allows it to operate in the most efficient manner and in the way it's supposed to. So you'll see some of the settings on your screen as far as how you can configure firmware, or more importantly, what are the configurations that come with your firmware. So this is probably not something you'll be configuring yourself. I want to go through a few more options because we have a continuation of this screen. And you can take a look at these and see what options are being configured when you install firmware or upgrade your firmware. So every time we boot up, your BIOS is accessed, your post is completed, your firmware is checked, and depending on what type of environment you're in, you may be going through a normal boot or this thing called a secure boot. So this is available in newer computers where UEFI 2.2 or later is available. And this prevents any of your drivers from loading that haven't been signed with what's called a key. This basically means if it's not vetted and approved by your operating system, it's not going to let the driver load. So it's trying to pretty much protect you from corrupted files, viruses, or any type of malware. So in any of the newer systems, it is defaulted to go through this process for the secure boot. You'll actually need to disable it if you don't want it to happen. But what did this look like before we had the fancy UEFI? You guys remember BIOS? This is what a BIOS screen looks like if you have never seen one before. And there are different BIOS manufacturers, so you might be used to a blue background with gray text, or like on screen, the gray background with the blue text, just depending on what manufacturer of BIOS you had. To access your BIOS on older computers and even some newer systems, you will find yourself hitting whatever key is the magical access key a bunch of times until the screen comes up when you restart your system. Meaning, you remember when you would shut your system down, restart it or bring it back up, and then start hitting the escape key or the F2 key, maybe F10 or F12, just back to back to back to back to back as fast as possible so that you didn't miss that very quick moment when you were able to access this. This is the screen that's behind that magical button. And there are a lot of settings that are housed back here, important stuff about what RAM is being used with your computer, what drive your computer should look at to find the operating system. You can actually change that here. So if you want to boot from a USB instead of your internal drives, or maybe you have an operating system loaded on some type of external storage, you can boot from there instead of from its native or default, which is going to be inside of your computer. The first time you ever load an OS, by default, it used to actually be looking at a CD or DVD drive, and now it's just looking at an internal hard drive by default. But lots of things can be changed back here, how fast your fans are running. You can actually set some passwords back here, all kinds of good stuff. So when we take a look at our firmware monitoring, we need to know in our BIOS screen what all this good stuff is looking at. Remember I talked about your fan speed? Well, we also can control at what temperature the fan actually comes on at. What is too hot? If you're living in a desert area that's 100+ degrees, you may actually want to lower the temperature where your fan kicks in so that it's on more often or earlier in the process. If you live in a place where it's super, super cold and you're iced out most of the year, you might want to back off your fan speed because you don't want your computer actually getting too cool. Intrusion detection is always fun as part of security, and I love talking about that. But at A+ level, it's really, really surface. So all we're going to talk about here is the fact that if somebody is trying to physically tamper with your computer, intrusion detection will alert you or whoever you decide to be alerted that the case is being removed. Now, there's two different ways. There's a live intrusion detection, which means somebody will tell me immediately. Or there's something as easy as like a piece of tape or a special sticker that will be ripped in half. So I'll know that somebody tampered with it, but I might not know who or when. So you have to think about what happened, and if so, what tools do you need to put in place? Maybe recording the room that your computers are in, having a CCTV system, or a live detection system which tells you immediately that somebody's tampering with your hardware. So let's move on to other cool stuff. Your voltage is just how much power is going through. Your system clock here is legitimately the time down to the millisecond. So just keeping time, which is why your CMOS battery is so important, because everything time-wise needs to be in line or nothing's gonna work. And the bus speed that we talked about earlier, which is how fast data can make it across your motherboard. So some cases you'll need to monitor the bus speed to make sure that your CPU speed is in line, but that's only if something is going wrong. So this is one of the first places you'll start troubleshooting if you're finding that your CPU speed or your data is not being processed properly and dropping off. On the hardware side, this is a good place to start looking. So the tools that you will need to take a look at some of this good stuff. First and foremost, a screwdriver. That is the starting point for any IT toolkit. And let me make a quick note, not the kind of screwdriver with a magnetic end. That's the kind that will get you in lots of trouble. right? We do not want magnets in or around our computer. So please make sure that any screwdrivers you're using are not magnetic tipped, and also the right size screwdriver. You might need those really, really tiny ones that work on like eyeglasses, because we have small screws in our hardware environments, especially on our motherboard. So anytime you need to access inside the computer, you'll need a screwdriver and whatever other tools appropriate, maybe an Allen wrench or a star to get in that thing. But on the operating system side, if we're looking at doing some troubleshooting from on our screen instead of with our hands, then we can use the command prompt, that black screen with the white text where we put in like ipconfig, and we can do some cool things, and I'll actually bring one up on screen so you can see what I'm talking about. These are some of the tools that you can actually put in to troubleshoot disk issues. So check disk, boot rec, disk part or disk partition. You have format, and your F disk is going to help you create different partitions. So while we're talking about this, let me bring up a command prompt and throw it on your screen. Here we go. So this is a command prompt. You can see that I'm logged in as the portion of my name. That's my computer name at this time. And I can put some information in here and bring up all kinds of different things. So that's a net command. I can use an ipconfig command and get information about my IPv4 address and my MAC address. I can put in some of these check disk or boot rec commands here. I wouldn't recommend playing too much in here unless you know what you're doing. But if you'd like to, one of the easiest ones, and where you cannot get yourself in trouble, is ipconfig. No spaces, just ipconfig, and hit enter. And you'll see all kinds of really cool, fun information about your own system and your own internet connection. So with that being said, let's jump back into disk issues and how we solve all these crazy things. Here's a list of some of the most common symptoms that you're having a hard drive issue. So when something bad happens, you need to know where you should be looking to fix this thing. Post errors, meaning those beeps, can definitely happen. Now, of course, the most common for post errors is the RAM issue, but that doesn't mean it's the only kind. You can have a post error for a hard drive issue. If you have hard drive disks, not solid state, but the ones that actually still rotate, and you have a really loud noise, whether it's clicking or grinding, I would turn your computer off immediately, because the longer you let that happen, the more damage is going to happen to your drive, which means you're less likely to be able to recover any of that data. At the bottom of that list, you see Bsod, and that stands for blue screen of death. Now, there are two things I want to say here. First and foremost, blue screen of death is not always the end of your computer's life, but it is probably the end of a component. So it should give you on screen some type of message that tells you what you need to go check. The second thing I want to tell you here is that a blue screen of death is blue. It is not going to be a different color. It's not going to be red or yellow or green or purple. If something like that happens and it's a different color, that's probably ransomware or some type of trick being played on you. Now, can you think of one reason, and there is one legitimate reason, that the blue screen of death might not be blue? Think about it for a moment. All right, what's one thing that could break that could make what should be blue not blue? And that's actually going to be your graphics card or your monitor. If for some reason your graphics card is failing, it may not give you a blue screen of death. It will either give you a different color, or your monitor is going to have zero screen being displayed at all. If your graphics card fails, it cannot show you that it's failed on your screen, because that means it's no longer to display on your screen. So that is the one case that your Bsod would technically not be a blue screen of death. It will either be a random color if for some reason a color is not being sent properly, but most likely your screen's just going to go black. So we learned about RAID, and like I said, I'm going to put on screen those different versions, and that will give us an opportunity to revisit what all this even means. But I do want to talk about some RAID-specific issues. A lot of times we will come across, especially if there's been a firmware update or any changes in our drives, that our computer will not boot up, and it will tell you that it doesn't recognize the drives. And that just means that it needs to be reconfigured. You need to tell it again that there is a RAID there, that there are multiple drives, and there's a certain configuration that it needs to take a look at. Most common things, but that usually only happens when some type of update has been made. So the second thing that happens here is that your RAID was detected. You booted up just fine, but then it stops working suddenly in the middle of everything. So either a setting has changed within the system or the firmware, or another configuration has been changed. Sometimes a component that the RAID is dependent on has changed, and not necessarily that it physically has moved, but there's some type of configuration or diagnostic change within it. The other thing that could be happening is that there's a driver issue. If you have a system where your drivers are being updated automatically and there's a change in the background, it could trickle down and affect your RAID being able to operate smoothly. So make sure that when you're in an enterprise environment, meaning big business, thousands of computers, process to have all of this under control. So if you're going to have updates going on in your system, first and foremost, those updates should be happening during close hours or during some type of maintenance window. But nonetheless, know that those updates could affect other things, like the drivers for your actual drives, which are how your RAID is made. And then if that is not compatible with your RAID controller, then something's going to go wrong. They may not recognize that RAID is still there. So just kind of be aware of those details. Don't let them overwhelm you or escape you, because when you start troubleshooting things, you're going to want to know where to look to pinpoint what the issue is to get it fixed. So the last section that we're going to cover here before we jump into the RAID examples are monitoring. Every time we have something going on in IT, as far as somebody logging into a computer, opening an application, whether they are interacting with a website, everything is logged somewhere. And all of those logs and all of those diagnostics are going to fall into certain GUIs or graphic user interfaces, which means we can bring them up and we can look at them. The rule here is that we want to make sure that all of our components are monitoring themselves, meaning they're showing you, the IT rep, diagnostics at all times, and that they are able to be analyzed so that if you ever have more questions about them, that you can jump in and get more information. And you want to make sure that they're reporting appropriately and in a way that you can understand. There's no purpose in keeping logs of something and using them for troubleshooting tools if you have no idea what's on these logs. So make sure, and it's called a SMART system, self-monitoring, analysis, and reporting technology, meaning that your components are diagnosing themselves consistently, giving a report to you, and that you can understand that report. If for any reason this is not the case, you might want to take a look at some third-party options or some different ways to monitor all these components so that when things do go wrong, you have a realistic, feasible way to react to it in a timely manner. All right, so let me put this on screen for y'all for just a little bit. I'm going to pull up a place where I can draw out our RAID so you can understand that better. So right now, take a quick 5-minute break while I get that all set up for you, and we will get it on screen. I've got it all set up to draw on my screen for you, and we're going to do really, really pretty Pictionary with RAID levels 0, 1, 5, and 10. So I'll share my screen here, and we will get started. That's always fun. All right, so when we are taking a look at RAID, I want to first draw out RAID 0. And let's actually label that a little bit better. Okay, RAID 0 requires 2 disks, 1 and 2. And this is what's referred to as striping. So as we put data on these disks, we are going to stripe it across. Data piece 1, data piece 2, data 3, and data 4. Well, that's super fancy, but didn't quite work the way I wanted it. But you understand the idea there. So let's try and redraw those a little better. 2 and 4. Beautiful. So we don't have any redundancy here, but we've increased our performance. So we're striping the data. We put data, a piece of data on the first disk, and then we put another piece of data on the second disk. We put the next piece of data on the third disk. So our write speed, we have read speed and write speed for our disks. Our writing speed is increased because we can put it in 2 different places and be working faster. Our read speed is going to be even more diverse or faster per se, because we have 2 different disks that we're able to draw that data from simultaneously, which means we can do twice as much at a time. RAID 0. Let's now look at RAID, there we go, 1 with my beautiful on-screen drawings here. So let's increase this. So RAID 1 is also going to require 2 drives. And this is going to be called mirroring. So when we have mirroring, we're going to make an exact copy of the data on both disks. That means, make this a little bit smaller. That means we have the pieces of data of 1, 2, 3, and 4 all on one disk, and we have an exact copy of it right next door. 1, 2, 3, and 4, my crazy 4 there, are all going to be on the same disk, on both disks, so that we have redundancy in the information. There we go. So you see the difference between RAID 0 and RAID 1. On RAID 0, we have striping, and RAID 1, we have mirroring. And RAID 0 is going to give us an increase in performance only. RAID 1 is going to give us an increase in redundancy only, but we haven't benefited from both redundancy and an increase in performance quite yet. So our next layer of RAID is going to be RAID 5. Now this has a requirement of how many disks? 3. So we're going to have 1, 2, 3 disks at a minimum to run RAID 5. Now this is the one that we can refer to as striping plus parity. It still stripes data. So let's say we now have 6 pieces. 1, 2, and 3 pieces of data. That doesn't look beautiful. Let's try that again. All right, 1, 2, and 3 pieces of data, and then we have 4, 5, and 6. So our data is still striped. That's great. So we have an increase in performance. But where does the redundancy come in? Well, this is how parity works here. Let's put just a little extra section on each one of these disks. And this is where we will hold parity information. Now, not that physically you'll have a little tail off of the disks, but you'll have a section on the disks that's specifically for holding the parity information. So how this works is, let's say on disk A, we'll label that one A. I'll have to write better. Okay, let's try that again. We'll label this one disk A. We'll label this one disk B, and this one disk C, just to not get confused with the numbers. So on disk A, we have data 1 and 4. On disk B, we have data 2 and 5. And on disk C, as in Charlie, we have data 3 and 6. So on the first disk, we want to hold some parity information from the other 2 disks. That way, if one of the other 2 disks fails, we can start to rebuild that information using the parity. So on disk A, we will hold parity information for 2 and 3. On disk B, we will hold the parity information for 1 and 6. And on disk C, we'll hold the parity information for 4 and 5. Kind of. So you get the idea here as far as where the numbers are placed. So how does that work and why does that work? Well, if for any reason, close enough. If for any reason our Bravo disk fails, okay, then we have now lost the data for 2 and 5. So we go get a new disk and plug it in, and we need to rebuild this data. We're going to use the parity information from disk A to rebuild 2, and the parity information from the Charlie disk to rebuild the information for data of 5. And then you put that disk in the place here. All right, you're just going to shoot that little guy into its spot, taking the failed disk out, putting the new disk in, and you'll have your normal RAID array back. So now I get to draw all that fun stuff again, where we have our Bravo disk, and we're going to have pieces of information for 2 and 5. And then we're going to start also rebuilding our parity information for both 1 and 6. And I'll redraw that there. So that's how RAID 5 works. 3 disk minimum, striping of the data, plus parity to rebuild data if a drive fails. So RAID 10 is our last one. And we'll see if my drawings get any prettier with all of this practice. Now RAID 10 is RAID 1 plus 0 is the best way to actually understand how that works. And we need a minimum here of 4 disks. So let's draw 4 of those. And if you have a piece of paper, this is a great time to make your own notes of all of these pretty little circles and see how this works, because you will be studying this outside of the videos. You'll see questions about this on your exams. So let's take a look at how we can combine RAID 1 plus RAID 0. So I'm actually going to start with the concepts of RAID 0 first, and then I'll go into RAID 1. We need to name our disks here just for clarity. So again, I'll go with letters: Alpha, Bravo, Charlie, and Delta disks. That D doesn't want to close. There we go. Let's see if I can try that again. All right. Beautiful. And on our first disk, our alpha disk, we're going to have the first bit of information. On our Bravo disk, we'll put second. On our alpha disk again, we'll put our third section of information, and on Bravo, we'll put our fourth. So we see RAID 0 has completely been applied and duplicated itself here. So now we need to create RAID 1, which gives us some mirroring. So again, in Charlie and Delta, I'm going to make a copy of our Alpha and Bravo disks. So on Charlie, I'll have information from 1 and 3. And from Bravo, I'll have information, on Delta, I'll have information from 2 and 4. It gives us the ability to continue operation even if we have a failed disk. In RAID 0, how many disks can fail before you lose information? All right, so thinking about that, you're kind of like, I don't see how a disk can fail at all. You would lose information no matter what happened. And that is absolutely correct. If one of our disks failed in RAID 0, that information is non-recoverable because the 2 and 4 pieces of data are not anywhere else for us to recover at this point. That means we have 0 redundancy, and that's not good. Now, can you have any disks fail in RAID 1 and still continue operation? Well, the answer is absolutely. If the second disk failed in RAID 1, we could still continue operation because all of our data is on the first disk. 1, 2, 3, and 4 are all there. Our troubleshooting at that point would be to go buy a new disk to replace the one that has failed, and then rebuild the copy of the data. But at no point in time would we have to stop our operations because of the disk failure. Now in RAID 5, can a disk fail? And how do you get the information back? All right, I'm not going to redraw the full process because I know we did that before, but if we do have a disk fail, and let's call it Charlie disk in this instance, we can replace our data. However, we are going to have to stop operations for a bit until we buy a new disk that we can then rebuild that data on. So yes, we can continue operation, and yes, our data is retrievable, but we will have some slowdown or some pause in what we're doing. Now in RAID 10, how many disks can fail without losing any information at all? All right, if you said 1 or 2, you are technically correct. 1 disk can fail, and we can continue operation because we have all that data on the B disk. If Delta disk fails, we have all that information there on B. Now, if you said 2 disks can fail, you are right, but there's a contingency there because Charlie disk can fail and we still can rely on Alpha. That's fine. Not a problem. Oops. Not a problem for that because we have all the data. We would purchase 2 new disks and we'd implement them. However, let me erase these marks. If for any reason our Charlie disk fails and our Alpha disk fails, where do we go get information 1 and 3? There's no way to retrieve that. There's no way to recover it. So 2 disks can fail in RAID 10, but they can't be the mirrored disks or the pair that matches. They have to be 2 that do not match as far as the data that they're housing. If you have any questions about that, please put them on your Google wall so I can try my best to explain. I am going to jump back to a normal screen. Awesome. So we've made it through different type of storage mediums. We've made it through RAID, which is not the easiest thing to understand. There are 4 different kinds. You need to study them. There are actually more than 4, but those are the primary ones that will be on your test. I want you to take a minute, take those notes, go back in the video and rewatch that section if you need to, but take a blank piece of paper and honestly, write it all out. Put 1 disk and 2 disks, and then 1 disk and 2 disks for RAID 0 and 1. Put your 3, draw out your parity, and of course all 4 for RAID 10, and practice that stuff out. The more you write down, the more information is going to be actually held in your head and not just falling out the other side. So even if you know some of this stuff and it's just a new acronym here or there, please write it down, please make flashcards, and do your best to make sure that you're ready for these tests and you're ready to apply this knowledge. The more you write, the easier it'll get. So I'm going to end this, prep another section for you, and I will see you back here very soon.